There are many real-world examples of things that grow or decay exponentially. And today we're going to just be looking at one of those examples, and that's a compound interest situation. So I'm going to take this compound interest situation and I'm going to show you the exponential function and how to problem solve, as well as the log function and how to use that to problem solve. So before we do though, we do need to know one thing, and that's the formula for compound interest. So if in a compound interest situation, so you put your money in the bank and your money is growing, the formula for that is future value equals present value, which is the starting amount, times 1 plus the percentage of interest per year over 100K. And that K is how many times the bank is calculating your interest per year. I'll write all this down so you have it. Raised to the NK. All right. So again, FV is future value. So what you end up with. PV is starting value or present value. R is the percent interest per year, so I'll just put the sign here, percent per year. K is compounding periods per year. So for example, if it's a monthly calculation, K would be 12. So I'll just say compounding periods per year here. All right. And what else do we have? Oh, and finally, N is the number of years. All right, so for example here, I can have an account. Actually, let's turn the page to get some space to work. Okay, so you have an account. You deposit $5,000 into it at the start, so that's your present value. And you have an interest rate, R, of 2.75%. Compounding monthly. Monthly is 12 times per year. So the K value is 12. And we want to know how much is in the account after 5 years. 5 years is the number of years, N. So we are now looking for the final value, or FV. So let's plug in to our exponential function and see how it works. All right, so we have FV equals, and I'm just rewriting the formula here, PV times 1 plus R over 100K to the NK. FV is what we're looking for. We don't know it. Is PV, that's our starting amount, which is 5,000. 1 plus our percent interest per year, so 2.75 over 100. And our K, since it's compounding monthly, is 12. Raised to, and here's the exponential part, NK, so N is 5 because it's 5 years, times K, which we already know, is 12. All right, so this is an exponential function because we are raising it to an exponent here to calculate what we need to find. All right, so our final value when we type everything into our calculator, if you do it correctly, you should get $5,736.11. All right, so that's how that works. But it's the logarithms part that I really wanted to get to because it's really cool to figure out how to solve for an exponent using logarithms. Okay, so we're in the same bank, we have the same interest rate, we have the same number of calculations per year, 12 calculations per year monthly, and our money is growing, right? So we're happy, you know, we ended up with $5,700 and something, and we're like, oh, that's kind of nice, but we're trying to retire here. We want to know how long it will take our money to double. Well, obviously we can't retire on $10,000, but you know what I'm saying. This is the type of calculation that we're trying to do here. How long would it take for an account starting at a certain amount to get to a certain amount? So this is awesome. We don't have to just keep trying different numbers and try, guess and check. we can actually solve this very accurately using logarithms. So let's go ahead and start doing that. Rewriting the formula, we have FV equals PV 1 plus R over 100K to the NK. Alright, so remember that N is the number of years and K is the number of compounding periods per year or number of months per year. So overall, this NK really just means number of months. So I'm going to replace that with number of months. Alright, so here we have our future value. We want our money to double, so our future value is therefore 10,000. And we're starting off with our present value of 5,000 times 1 plus R, the percent interest per year is 2.75 over 100, and it's compounding monthly, so 12 to the number of months. All right, so now we have an exponent as our unknown. Whenever we have an exponent as an unknown, we can use logarithms to solve it. I'll repeat because it's important. Whenever you have an exponent that's unknown, we can use logarithms to solve it. So how do we go about doing that? Well, first of all, we want to simplify as much as possible. So according to our order of operations, what should be simplified first? If you said or parentheses, that is correct. So we get 10,000, and I'm just rewriting that over here, is equal to 5,000. And when we simplify these parentheses, we get 1.0022917 raised to the number of months. All right, notice here that I've used so many decimal places after our decimal point. The reason for this is because we're going to raise it to a large number of months. There's a big difference between raising 1.00 to a big number and raising 1.0022917 to the number of months. So I'm using 5 digits after my last 0. I would advise you to do the same or even more. Okay, at this point, we can still do one more thing to isolate our expression with our exponent. We have 5,000 here, and that's not being raised to this power. So I can actually just go ahead and, to get rid of this, divide both sides by 5,000. So on the left side, we have 2, and on the right side it cancels, and we have 1.0022917 raised to the number of months. All right, so whenever we have an unknown exponent, we totally can take the logs of both sides. What does that mean? I'll show you right now. So if I take the log of this side and I take the log of this side, it will help us to solve the problem. Now, recall that in logarithms, the third law of logarithms tells us that we can take an exponent and move it over here to become a coefficient. The third law of logs allows us to do that. So on the left side, we have here log 2 is equal to the number of months, which we don't know yet, times log 1.0022917. All right, so before we had a logarithm that was unknown, which how would we ever solve for an unknown exponent? Sorry, we had an exponent. How would we solve for an exponent that we don't know? Well, now we have a coefficient that we don't know. And I think all of us know that in order to solve for a coefficient here, all we have to do is divide by this expression. And of course, what we do to one side, we have to do to the other side. So now we can isolate the months. 1.0022917. So we're dividing both sides by that log. So that divided by a log of 1.0022917. All right, so once we do that, we get that the months is equal to This log over this log should give us 237.97, approximately 237.97 months. And that's the number of months it will take $4,000 or $5,000 to double. If you wanted to find out the number of years, you could do that, of course, by dividing the number of months by 12, and you'd get approximately 20 years. So it would take 20 years for $4,000 or $5,000 to double. Awesome.